Hello students, welcome back again. In this part, we will discuss about Lenz law and its application as conversion of mechanical energy into electric energy. Then we will discuss about the drawbacks of Lenz law as eddy currents concept. Then we will discuss about the application involved in the eddy currents and then self-inductions. And the best example of self-induction, finding self-induction of a solenoid. So let's start this. Let's discuss about Lenz law. In case of Lenz law, we will discuss about law of conservation of energy. So, the statement is about the principle stated that an electric current induced by a source such as changing magnetic field always creates a counter force opposing tendency force with the force that magnet is induced in. Or we can say the law accounts for such phenomena as diamagnetism and electrical properties of inductors. So we can assume there is a magnet having two pole, north pole and south pole, that brings into the coil connected across the galvanometer. So when we are bringing magnet, the movement is against the repulsion. So that repulsion is just due to the Lenz law. It predicts the concept of Lenz law. So when you take magnet away from the coil, that repulsion is just reduced. So this is associated with the induced current produced in the secondary coil due to the induced EMF would be of opposing tendency that creates it. That is created by the relative motion of the external coil or external magnet when this strength is passing through the area of the secondary coil. So, and its nature would be of opposing tendency. This is under Lenz law. Now the second statement and the examples we can consider here, that Lenz law stated that induced current always opposes the flux that creates it. Mean you can say this is an external magnet and there is a current carrying coil. It is like a solenoid. Solenoid is like when wire is wrapped over a material, then lines of force passing through the core it just behave like a solenoid. So when we bring magnet towards this coil, what happens? The deflection produced or reflected by the galvanometer will be according to the relative motion of the coil. Secondary, when we are taking magnet away from the coil, the strength of the magnetic induced EMF is just decreased. Similarly, when we are taking or when we change the polarity, we found the same counter effect. So the point is that this EMF E is due to the change of magnetic flux with respect to time c. Already we discussed that electric current or induced current in the coil is just due to the EMF, and that EMF is due to the change in magnetic flux. Also the number of turns, means you can see the coil having n number of turns across which the magnetic lines of force is passing, and due to the relative motion it shows electric current. So point is that the nature I means the symbol I, this symbol I, symbol negative symbol, this is what opposing tendency. So mean we can say I is the induced current in the coil due to the change in magnetic flux in the secondary coil when we bring magnet towards it or taking magnet away from the coil. So this would be of opposing tendency. Now what are the applications? Its application involve law of conservation of energy. Means the small amount of work is done like bringing magnet towards the coil or taking it away from it. So due to that motion, an induced EMF would be there across the secondary coil, and due to that EMF there would be electric energy across that coil. So we can recite it like a small amount of work therefore is done in the pushing the magnet into the coil and in pulling out against the magnetic effect of this, and this causes induced current in the secondary coil. Now the small amount of energy represented by this work manifests itself as a slightly heating effect. So we know that 100% energy is not converted into that part. Some percent of energy can be as wasted in the form of heat energy. So this is it, and this results of induced current encountering resistance in the material of the coil. This is under Lenz law, and in this way we can say law of conservation of energy take place. Work done by the external agent is equal to the electric energy induced across the coil along with the heat production. So this is the example. We can say there is a person trying to connect this. This is an external DC source, we can say. So what? This is a galvanometer source. So amount of work done by this person. So this deflection, this is the deflection sourced by the galvanometer. When we connect the wire, its nature would be of opposing tendency according to Lenz law, and when we consider its magnitudic part like conservation of energy, so amount of work done would be equal to the energy dissipated across the secondary coil along with the heat production. Now, when we are talking about eddy current production, when talking about induced current, some drawbacks associated with this is also in the eddy current. What is eddy current? Eddy current, how it look like? We can see the diagram. This is a tornado kind of, a circular kind of circuit, produced across the metallic part. This is the metallic conducting part, and this is copper tube. It's secondary magnetic field, primary magnetic field. So point is that there are two words written over here. First is primary magnetic field, second is secondary magnetic field. How secondary magnetic field is produced and what is the use of it? Is it responsible to produce induced current in the secondary coil? Of course no. This secondary current produce or induce eddy currents across the conducting part, and this is very harmful. So we need to understand, when current is induced in a bulk piece of conductor, the induced current often flows in small circles that are strongest at the surface and penetrates a short distance into the material. This current flows pattern are thought to resemble eddies in a stream, which are the tornado liquid swells of water that we sometimes see. Because of this pre-assumed resemblance, the electric currents were named eddy currents. So eddy current is like, in Hindi we called it bhavar, like so means the current across the metallic part due to the secondary current, secondary magnetic field produced is just, and this is very harmful. And how can we avoid this one? By laminating the coil. So it is there, these circulating eddies of current have inductance and thus induce magnetic field. These fields can cause repulsive, attractive, and heating effects. So mean eddy current is the secondary current, causes back EMF, and when this current is flowing across the metallic part and that metallic part is having some resistance, definitely there would be heat production, and this heat is the reason that 100% energy conservation means work done by external agent doesn't convert into the heat electric energy across the coil. So amount of energy produced across the eddy current causes heating effect. Now eddy currents are undesirable as they heat up the conductor and dissipate electric energy. So we want to avoid these eddy currents produced across the secondary coil, maybe like transformer, maybe like induction motor, maybe like generator we have. So what we do to minimize these current, we try to minimize the eddy currents by laminating the metallic or by cutting slots. So mean we are cutting slots like that, or we can say this is a metallic part, we would like to laminate it with a plastic coil and then we will wrap a wire over it. What will happen when we allow magnetic lines of force passing through that area? EMF produced causes electric current, okay, and that is secondary electric current. But we also seen that secondary coils get heated up. It is due to the eddy currents. So if we want to avoid that heating, we need to laminate the plastic or the insulating material without affecting the induction phenomena. So eddy currents produced in the metallic part. due to the flux induced in the secondary and due to the current in the primary. So we can say, if we consider two coil 1, coil 2, we want to see any change in the secondary. So we will allow electric current in the primary. Due to that, magnetic lines of force will also pass through the secondary. When there is a relative motion, flux produced. Due to that flux, induce EMF and then induce current. So due to that induced current, some peak back EMF is produced. It causes eddy currents through the current metallic part, and that heat the system, that got heated, that produce heating in the system, and we can avoid it by eliminating the coils. Now we need to understand what is induction. So induction we already discussed. Now self-induction. Self-induction is the effect in which a changing current in a coil induce an EMF in the same circuit as known. So main point is that we could know that whenever we have time varying we have time varying battery source, maybe AC or maybe DC. So when electric current will pass through this wire that is wrapped over an insulating material, then due to this wire, magnetic lines of force will pass. So the question is, what is self-induction? So self-induction is the inducement of current across the secondary coil, inducement of current across the secondary coil due to the magnetic flux of primary one. So mean the effect in which a changing current in the circuit induces and EMF produces in the same circuit is referred to as self-induction. Mathematically we can express it like this one: E is equal to minus of L d phi by dt. So EMF produced is equal to minus of L into del I upon del t. Means current is changing with respect to time t. It's just EMF across it. So we can say, when we allow rheostat, it is a variable resistance connected across this battery, and this is a key. When we allow electric current to pass through this, magnetic lines of force is produced. So we are getting, there is a change in the, means when we are changing resistance, definitely current will change, and due to that current, variable current, due to variable resistance, their EMF will produce across the secondary coil. EMF will produce across the secondary coil, or we can say the coil we connect across it is equal to, or it is directly proportional to the variation in current delta, because variation is just due to the variable resistance, and there would be like voltage drop in Ohm's law. So we are discussing self-induction. So if we need to understand that coil must have its own inducting phenomena, that is denoted by this di by dt. So to remove that proportional sign, we are putting here EL is equal to L into di by dt for a short range, for an instant values. Or we can change this variable current with the rheostat we have, or with the AC source, because AC current is just time varying current. So we can allow through this, we can sense the effect of self-induction. L is the coefficient of self-induction change, and delta I by delta t change in current values. Now mathematical part, if we want to find out self-inductance of a solenoid, so we can say these effects are called self-induction. I will discuss that. The EMF that is produced is called self-induced EMF, that is denoted by E equal to L del by del t. L is a constant coefficient of self-induction, and usually L is represented in Henry. Now minus sign indicates the changing current induces an EMF that is of opposite tendency. Negative sign is just about the nature of opposition. Now an expression from the induced EMF can be found out by this E is equal to minus L del phi by del t. So we can put E, it can be also equal to change in flux, that is N into del phi by del t. Okay, so when we change this value, finally we are getting L is equal to this relation, and it depends on the flux produced in the secondary coil. This is what magnetic flux due to the current, and N is the number of turns. So we get L is equal to N phi by V, and easily we can understand it like how to get self-inductance of a solenoid. So we must understand phi is equal to magnetic field into the area, and we must understand what is the magnetic field of a solenoid. Already we discussed that is equal to mu into n into I upon length of the solenoid. So when we put this value over here and area is given already, so we are getting mu naught n square A into current upon length of the solenoid. But we know that magnetic flux is equal to self-induction coefficient multiplied by area. So we need to put these quantities equal to each other, and finally we are getting a mathematical relation L is equal to mu into n square A by L. Now some applications part we can say L is directly proportional to the n square and inversely proportional to current we have. Okay, other quantities are constant. And how can we represent equal? That is this one. So this is what the inductance given by L, and we can say the potential or means EMF across this is equal to minus of L di by dt. Or when we want to know its magnitude, we need to take it modulus, so that is equal to L di by dt. This would be used to find in the case of transient current. Now these are the examples we can solve. The first example, an electron is moving in a circular orbit of radius r with an angular acceleration alpha. At the center of the orbit is kept a conducting loop of radius r. Then EMF induced in the smaller loop due to the motion of the secondary. So easily we can understand that if there is current carrying coil of radius r, so what if we are placing another coil of having radius small r? We want to find out EMF induced in the smaller loop, induce EMF in the smaller loop. So we must understand this EMF is equal to delta phi upon delta t. So delta phi is change in magnetic flux. So change in magnetic flux is magnetic field due to the first one. This is coil number 1 and this can take coil number 2. So magnetic field due to 1, area of 2 if it is changing with respect to time t, delta A. So we know that magnetic field can be calculated due to circular current carrying coil is mu naught I upon 2r, because capital R is the radius and we want to find out its area, that is pi into r into square delta A by delta t. This way we are getting. So the point is E is equal to mu naught into I upon 2r into pi r square. Also the second term we need to understand, area we calculated over here. Now EMF induced in the secondary loop due to the motion of the electron. We know that angular acceleration is given, that is equal to d omega by dt. So electron, so we need to find out the value of current. So we know that current is equal to dq by dt. Now q is just the electron divided by capital T. So that is equal to E upon 2 pi r upon the velocity with which it is rotating. Now we can see that E upon 2 pi into omega. So when we will put this value of current over here in the main equation, we are getting EMF is equal to mu naught into pi into r square upon 2r into di by dt, because we couldn't conclude the value delta t, but we want to find out for a small instant change. So we will put E is equal to mu naught upon capital 2r pi r square into I is E into V equal to r omega. So we can also say E into r into omega by 2 pi r would be cancelled out. So that is E omega by 2 pi. So we can say E d omega by dt upon 2. So finally we are getting the relation as mu naught upon 2 r pi r square, also 4 d omega by dt into E and d omega t by alpha. So we are getting, means point we need to understand, this is the keyword used in the question. Also the magnetic flux formula, magnetic EMF, induced EMF, and now magnetic flux formula involved in this question. So in this way we can solve. Example number 2, we can consider a resistance 10 ohm, radius 10 centimeter, and number of turns is rotated at a rate 100 revolutions per second about its diameter, is perpendicular to the uniform magnetic field of induction. This is the magnetic field strength, the amplitude of the current in the loop. So amplitude. So we first of all we will note down the given terms, that is R is equal to 10 ohm, radius is denoted by small r, that is equal to 10 centimeter. We can convert into meter. 10 into 10 power minus 2 meter. Number of turns as 100. Rotated at revolution, that is what frequency? 100 revolutions. So we can say that is for. Now diameter perpendicular to the initial diameter is perpendicular to it, and magnetic field is given at 10 millitesla, that is 10 to 10 power minus 3 Tesla. The amplitude of the current, so we have to find current. So we know that when the coil is rotating, the flux involved will be equal to NBA cos of theta, or we can put it as NBA cos of omega into time t. Now we want to find out current. Current is equal to what? That is equal to EMF by resistance R, or we can say 1 by R into d phi by dt. We will consider its magnitude. So when we will differentiate, we are getting NBA omega of sine omega t by resistance R. Okay, this one. So now it is given that it is perpendicular to this. So sine 90 is 1, theta equal to 90 degree with that. So we can say I is equal to NBA omega upon resistance R. On substituting the corresponding values, N is given as 100, magnetic field is given at 10 into 10 to the power minus 3, area is given as pi r square, that is, it is pi r square, radius is given 10 into 10 to the power minus 2, and finally we are given the angular, that is equal to 100 revolution divided by the resistance, it is also 10 ohm. So on solving this mathematical term, we are getting this would be equal to 2 ampere. So the formula used here is phi is equal to NB cos omega t, and we will differentiate to get the EMF, that is equal to NBA omega into sine omega t. Now current I is equal to EMF by resistance R. We will put the corresponding values as theta and 90 degree. So we will get the value of current, that is as 2 ampere in this question. Ask IITians brings you a very good opportunity to paste your questions regarding the subject. What you need to do? In this part we discussed Lenz law and its applications, eddy currents, self-inductance, finding self-inductance of a solenoid,